Okay, so we're on slide 27 of chapter 3, trying to get through these problems. So we're doing percent yield. If we react 10 grams of glucose, the reaction is shown here at the bottom of the screen. If we react 10 grams of glucose and we do the reaction in the lab, when we finish, we collect all the carbon dioxide and we're able to weigh it, and we figure out that we produced 12.7 grams of carbon dioxide. How did we do? What was the percent yield? Did we do a good job or a bad job? That's the kind of thing that we're trying to assess here, okay? So what we need to do, we have to look at the numbers and decide what does each number represent. First of all, if we're doing percent yield, we have to be looking, percent yield is the equation we need. Percent yield is the actual yield over the theoretical yield times 100. So if I'm solving for the percent yield, the question is, did they give me either of these two values? And the answer is, if you read the question, they said that 12.7 grams of CO2 were collected. So that means somebody did it in a lab, they collected it and they weighed it. That's the actual yield. So the actual yield is 12.7 grams. Okay? Now the theoretical yield. Theoretical yield is like how much we should have made. They didn't tell us that. They almost never are going to tell you the theoretical yield, but they did tell me how much glucose I started with. Okay, now remember, the actual yield and theoretical yield, those should be values that are tied to one of the products, because it's the yield of the product. Okay, now there are actually two products for this reaction. There's CO2 and water, but we're only going to be focused on one of them. This problem is all going to be about the amount of CO2 they collected. So there is water being made too, we're just not looking at that. Okay, so the actual yield, theoretical yield should both be for CO2. They only gave me one of them. I need to solve for the other one. How do I solve for it? Well, I go back to the amount of starting material. They said that there are 10 grams of glucose, C6H12O6. I'm going to calculate the grams of CO2. Again, grams of A to grams of B, 3 steps. Divide by the molecular weight of the first one. Use the ratio 1 to 6 for the second one. And then the molecular weight of CO2 is 44. So again, I'm doing real shorthand here, but that's the overall calculation. So if I punch that in my calculator, I should have gotten 14.52 grams. Okay? So if the 10 grams of glucose reacted perfectly, the maximum amount of CO2 that can be produced is 14.52 grams. That is the theoretical yield. That's the highest value possible. Now, somebody did the experiment, they got 12.7. So we need to take that number and put it down here. The theoretical yield is 14.52 grams. And we need to divide that number by that number to get the answer. Now, I might have rounded off when I shortened my calculation, so I think I'm a little bit off in what it is. I got the percent yield is around 87.5%. If you got something really close to that, then we should be good. All right, next problem. We're going a little bit deeper into some of these problems. So on this one, they gave me a paragraph of information. It's a very similar problem to what we just did, but we've added a step onto it because they didn't give me a reaction. I had to be able to read that paragraph, come up with a reaction, and then do all the math. And you can see how for a student who hasn't practiced enough, this problem by itself could take 15-20 minutes. But on a test, that's not okay. So I have to go to read this and say, okay, student dissolves 10 grams of silver nitrate in water. That's not the reaction. So I'm going to have Ag with NO3 I know that silver is always +1. It's a transition metal, but it's one of the ones you have to remember. Silver is +1, nitrate's -1. So that's the formula. You dissolve it in water, so that makes it aqueous. And then you add a piece of copper. When they react, it forms aqueous copper 2 nitrate. So my copper, it says it's +2 because of the Roman numeral. Nitrate is -1. So the 2 on the copper goes on nitrate, so it makes CuNO3 twice. Aqueous. Plus, and then elemental silver is formed also, so that's Ag solid. So that's my reaction with the correct formulas. Now I have to balance the equation. I see 2 nitrates here, so I'm going to put a 2 over here, and then I have 2 silvers, so I'm going to put a 2 here. So that's my equation. You have to be able to get that quickly. Then I can start doing the math. So the question says I have 10 grams of silver nitrate initially. They do the reaction, and at the end they collect 5 grams of silver. So I would use the 10 grams of AgNO3 to calculate with 3 steps the grams of silver. That's going to be my theoretical yield. And then I have to do the percent. It's going to be the actual yield over the theoretical yield times 100. So whatever my answer is here will be the theoretical yield. The actual yield, they said they got 5 grams, so that's going to go here. And then that over that times 100 will be your answer. Okay, I'm going to leave that to you guys to finish up, but I don't think that'll be difficult based on the examples we've done. But the key here, there are a series of steps that we had to go through. We had to write the Malus equation first. You have to get that right. Now, on a test, if this is one where you get to show your work, and if you're online, you'll do your work on paper and then upload it into D2L, I will give partial credit based on what you do. So if you have to write the reaction and mess it up, that doesn't mean you can't do the rest of the problem. You can keep going. I'll give partial credit wherever I can. You just got to make sure that you show the work that you can, support your answers to see how many points you can get. Okay? But you write the equation, then we have to take the grams to calculate moles, then we do the mole-to-mole ratio, then we go from the moles back to the grams of the product. That's my theoretical yield. Do actual over theoretical to get the percent yield. All right, so one more big topic in chapter 3 is limiting reagent. All right, now, basically the idea of limiting reagent is that most reactions that we do involve 2 reactants. Okay, so when I put 2 reactants together, usually if I put them together in the perfect ratio to where they both get used up at the same time, that would be the perfect scenario where I can make my maximum amount of product and all my reactants get used. Excuse me, but a lot of times we don't put them together in the perfect ratio. Sometimes we just dump in 10 grams of one reactant and 20 grams of the other reactant, and we just kind of say, well, let's just see how much product we can make. Okay? So with any random ratio, what's going to happen is the reaction will keep going and make product until one of the reactants gets used up. When one of the reactants gets used up, the reaction can't go anymore. Okay? So an analogy for this is if you're making sandwiches. So if I go in the kitchen and let's say I'm making a peanut butter sandwich. So I need 2 pieces of bread and a jar of peanut butter. So in my pantry I've got a big jar of peanut butter that's full, and I got a loaf of bread, but there's only like 8 pieces of bread left in there. How many sandwiches can I make? Okay, well, if I have a big jar of peanut butter, it's like I've got plenty of peanut butter, so the peanut butter is not going to run out. Then that means the limiting reagent is going to be the bread. I'm going to use up the bread until I don't have any more, which if I use 8 pieces of bread to make sandwiches, everybody knows that means I can make 4 sandwiches. So that's a case where they don't even need to tell me how much peanut butter I have. I just assume there's plenty, and I'm going to use the bread. I'm going to make sure that's my limiting reagent. That's what I'm going to use to calculate the amount of product I can make. which are my sandwiches. Okay, now what about if I'm making a cheese sandwich, and let's just say a cheese sandwich, it's 2 pieces of bread and 1 slice of cheese. That's my cheese sandwich. What if I look in my fridge and in my pantry and I've got 8 pieces of bread and 3 pieces of cheese? How many sandwiches can I make? Okay, so what you have to do in this case, if they give you the amount of both reactants, the bread and the cheese, you kind of have to do 2 separate calculations in your head to get the answer. You'd think, well, if there's 8 pieces of bread, I know that I can use 2 pieces of bread per sandwich. So 8 pieces of bread divided by 2 is going to make 4 sandwiches. So I have enough bread to make 4 sandwiches. Then with the cheese, well, I'm only putting 1 piece of cheese on each sandwich. So it'd be the 3 pieces of cheese times 1 sandwich per piece of cheese is going to make 3 sandwiches. So I've got enough bread to make 4 sandwiches, but I only have enough cheese to make 3 sandwiches. What's the right answer? And the right answer is the reactant that gives you less of the product is the true answer. Once I make 3 sandwiches, I'm out of cheese. I can't make any more cheese sandwiches if I don't have any more cheese left. It doesn't matter if I have more bread. That'll be left over, which the one that runs out is called the limiting reagent. The one that I have some left over is called the excess reagent. I have more than I need, so that's the excess. All right, so when I have my reactants, when one of them runs out before the other one, that reactant is called the limiting reactant or limiting reagent. It's the same thing. The theoretical yield and the percent yield will be determined by that reactant. The one that had too much of, we know it can't all react, so basically you're not going to do any calculations using that number to get the amount of product. It wouldn't make any sense, because if I have 8 pieces of bread, it makes me think I can make 4 sandwiches, but I can't. That's a false number. It's not true, because I ran out of cheese after the 3rd sandwich. When you do it though, a lot of times people will look at like the numbers, and if it says 8 pieces of bread and 3 pieces of cheese, a lot of times people will just pick the smaller number and say, oh, there's less cheese, so it's the limiting reagent. You got to be really careful about that, because actually the mole relationships have to be considered. Imagine if I had 8 pieces of bread and 5 pieces of cheese. If you just look at the numbers, there's only 5 pieces of cheese. It seems like that's less. But you got to remember, it only takes 1 piece of cheese to make 1 sandwich. That's a 1-to-1 ratio. The bread is a 1 to 2 or a 2-to-1 ratio. So with my 8 pieces of bread, I make 4 sandwiches. With 5 pieces of cheese, I make 5 sandwiches. So even though I had less cheese in terms of the number, it ends up giving me more of the product. Okay, so you have to look at mole rate relationships, the ratios and stuff, before you make any quick assumptions. All right, so here's a reaction. I'm reacting carbon with oxygen, and I'm making carbon dioxide. So again, it doesn't give me the reaction, but based on the wording of the question, you should be able to figure out what the reaction is. And then from there, we can set up the problem. So again, I'm going to take this off the screen. All right, so my reaction, C plus O2 yields CO2. Now on the question, so I'm reacting 25 grams of carbon with 42 grams of oxygen. So just like we did with our sandwiches, I have to work a calculation twice. From my, let's call the carbons my bread and the oxygens my cheese. I have to look at my bread from the grams of carbon. I need to figure out how many sandwiches I can make, which the sandwich is the product. So I'm going to calculate from the grams of carbon, the grams of CO2 that can be produced, and then I'm going to do it again from the grams of oxygen to the grams of the CO2. So I have to figure out from both reactants, my bread and my cheese, I need to know how many sandwiches each one of them can make. And when I get the two answers, I'm going to pick the smaller one every time. Okay? So it's grams to grams. So both calculations are going to be the three-step calculations. Again, the problem gave me 25 grams of carbon and 42 grams of oxygen. We cannot just look at these numbers and just say, oh, 25 is smaller, that's the answer. Doesn't work that way. It might be, but that's like a 50-50 chance. So, first step, change grams to moles. For carbon, I'm going to divide by 12 because it's 12 grams per mole. Then the reaction is going to be 1C to 1 CO2. And then finally, to go back to the grams of CO2, 44 is the molecular weight of CO2 to 1 mole. So if I do that, if I use up all my carbon, 25, 12, I got 91.7 grams. So the carbon, if it all reacts, it's capable of producing 91.7 grams of CO2. Now for the oxygen, I do the same thing. I'm going to divide by 32. Then it's a 1-to-1 relationship between O2 and CO2. And then finally the 44 grams per mole. So let's punch it in. 42 divided by 32 times. So that one's going to give me 57.8. So when I look at these two answers, only one of them is right. Sometimes students will add them together, sometimes they'll subtract them, blah, blah, blah. It's wrong. You look at the two answers, the smaller one is correct, the other one is wrong. So in this reaction, if I mix these together, the best you could do is to make 57.75 grams or 57.8 grams or whatever it was. That is the maximum yield possible. That's what we call the theoretical yield of this reaction. All right, so we got one more problem. Oh, but I'm over, I got to cut off.